I will present you the first speaker, who is a person you have never seen at all today. His name is Giuseppe Sarracino, from the Astronomical Observatory of Rome, but also a little bit of Capodimonte. He will present his works about quantum Markov chain Monte Carlo for cosmological functions.
Okay, so I'm presenting to you something which is a little bit different from what you are going to see in the rest of the school, but it's just to show you, talking about possible new technologies that can be used in astrophysics and cosmology. My work which is all about quantum Markov chain Monte Carlo methods for cosmological functions, in particular BAO, CMB, supernovae 1A, an application of, in general, quantum computing to these cosmological proofs. So just to give you a little bit of an idea of what is our scientific background, so why it is important to investigate cosmological parameters? Well, first of all, according to the lambda CDM model, up to 95% of our universe today is made up of stuff that we do not know anything about. So dark matter and dark energy. And this has been told us by observations of cosmological parameters, like, for instance, the accelerated expansion of the universe that has been observed via the supernova type 1A. Another issue, which is more observational, if you want, is the problem of the Hubble tension, which is the fact that different cosmological proofs are giving you different values for the Hubble tension. In particular, you have the tension between the so-called early type measurements, so the ones that are related to the CMB, and so the early stages of the universe, and the late type ones, which are the ones related to the so-called cosmological ladder, so supernovae 1A, classical Cepheids, and so on and so forth. The problem is that adding more and more measurements to the Hubble constant is increasing the tension, is not alleviating it, and so one has to understand what is going on. So this is why in 1 minute it's important to understand what are the cosmological parameters and how to measure and detect and quantify them. So what is quantum computing? Well, quantum computing is a novel scientific discipline which tries to merge concept of quantum mechanics and computer science. The main difference between quantum computing and the classical one is in its information unit, which is the qubit that substitutes the classical one. So using the qubits that I will show you in the next slide what exactly is a qubit, one has to formulate quantum algorithm, so leveraging on the properties of quantum mechanics, one creates this algorithm to solve different tasks. Of course, one has to use quantum hardware to be able to run these quantum algorithms, so to use in a valid way these new concepts and these new properties that are not in the classical world. And of course, what is becoming more and more important quantum computing, because the quantum hardwares are finally being built in very recent years. Like, for instance, the quantum computer at the Federico II of Naples. So what is the qubit? The difference between the classical bit and the qubit is that the fact that while the classical bit can either be 0, either be 1 with 100% of probability, the qubit can be described on what is called the block sphere, which can be any possible superposition of the states 0 and states 1 with certain given probabilities. This has been possible thanks to the quantum properties, which is superposition. So the fact that as long as you do not classically measure a qubit, you can have any kind of combination of the probabilities of the qubit to be in a state 0 or 1, or a combination of the two. And also the entanglement, which is another different quantum property which relates to how the qubits behave one with the other. So I will not go too much into detail regarding this. If you are curious, of course, feel free to ask me during this school. I'm showing just to you a glossary of all the possible operations that can be performed on the qubits on what is called the quantum circuit. So given that each qubit starts from the state 0, you can perform this kind of operations, which are actually just rotational matrix, which change the state of the qubits. Each of these operations up to the control knot regard just one single qubit. So they all regard the state of one single qubit that start from 0 and then can be changed according to these operations. Then you have operations that involve two qubits that are described by matrices which are 4 by 4. And then the last operation, which is the Toffoli gate, which is the biggest operation that is possible inside a quantum circuit, which regards 3 different qubits. So, giving you a very brief introduction to quantum computing, this is a quantum circuit, in particular the quantum circuit that we have implemented inside our quantum Markov chain Monte Carlo. What is the idea here? The idea is that instead of choosing the steps using a classical method, one uses the steps inside the Markov chain Monte Carlo chains in a quantum method. Like, for instance, using the results given by the quantum circuit that I'm showing you inside this slide. So one uses this circuit to give you a new step in the chain, and then all the other evaluations are performed classically. So you see what is the value of the chain in the new position. You compare it with the value of the chain in the old one, and see if you accept or reject the step according the Metropoli-Hastings algorithm, which is the classical one that one usually uses. So this is the fundamental idea. We have applied it to cosmological probes. This first result regards just the CMB and a particular simplified likelihood related to the CMB. We used only the temperature spectrum here. And if you see only the contour plot, the GED contour plot, well, this is fine because actually inside this contour, in this figure, there are 2 different contour plots. The red, which is the classical NCMC, and the black, which are the results given by the quantum Markov chain Monte Carlo that we have implemented. The idea is that they have to give you the same contours because you use the same data and the same likelihood for both the computations. And any kind of difference is due to the samplers, and this is no good. So the fact that they are very similar one to the other means that how we have implemented the quantum Markov chain Monte Carlo with respect to the CMB actually works. And you can see it both visually from the contours that you see, from the one-dimension plots that you see for each cosmological parameters, and also for the correlation coefficient and zeta score that we have also computed. This is a new result where instead of using just the CMB, use CMB plus supernova plus BAO. And not only that, the CMB, in this case, we are using the full Planck likelihood because we have implemented our quantum Markov chain Monte Carlo method inside Cobaya in such a way that we can use the proper theory codes and the proper likelihoods code related to these cosmological probes. So these are again the results. We have also used to check another classical Markov chain Monte Carlo, which is MC. In red, instead, you see the contours for the quantum, and the blue, the results from CMB, and in gray area, instead, the one given you by Cobaya. You can see how the 3 contours, so again, in this case, you have 3 different contours for each plot, not just 2. The results are remarkably similar, given by the 3 different samplers, where again, you can see then that the classical and quantum are giving you the same results, giving reliability to the quantum results. This instead is a contour that has been obtained using the full CMB likelihood, considering all the nuisance parameters, not only the cosmological one, to see if our quantum Markov chain Monte Carlo actually is able to use to consider all these parameters. And as you can see from these results, you can see that in the vast majority of the cases, quantum and classical Markov chain Monte Carlo are remarkably similar in the results that they give you, which means that you can use also the quantum Markov chain Monte Carlo method also for a very complex case with a lot of cosmological parameters. So what are the conclusions? An hybrid quantum chain Monte Carlo has been built to find Bayesian contours for cosmological functions, so BRO, now BRO, CMB, and supernova type 1A. So these are the different probes and functions that we have used to test this algorithm. We have seen that the results are remarkably similar to the classical counterparts. Regarding the speed of the quantum Markov chain Monte Carlo, the main limitation is the fact that the more computationally expensive part of the Markov chain Monte Carlo estimations are in the likelihood evaluation, which also in the quantum algorithm remains classical, because the evaluation of the new step in the chain remains classical. So we do not see a speed up directly of the quantum with respect to the classical. One has to see if the quantum Markov chain Monte Carlo converges faster, so in the smaller number of steps that are required to reach a certain convergence level. These are the results up to now. The next step is to make new analysis with more complex parameter space and more cosmological probes. So thank you for your attention.
So thank Giuseppe. There are questions for him.
Can you explain your quantum circuit in a bit detail?
Yes. Let me go back. Okay. Yeah, okay. So as I was telling you before, each gate that you can see inside the quantum circuit involves one single qubit. The first layer is what is called the Adamant gate, which is a gate that given a qubit in state 0, gives you the perfect superposition of as a result of the states 0 and 1. So the probability after given a qubit 0 and then applying another Adamant gate, if you measure it, you have 50% of probability to find 0, 50% of probability of finding 1. Then you have all rotational gates, 2 layers of rotational gates on two different axes, the X and Z axis of the Bloch sphere, that change again the amplitudes related to the states 0 and 1 because they rotate the qubit on the Bloch sphere. Then you have what are called controlled rotation, which are rotation which involve this time 2 different qubits. So you have the first step, which is a controlled knot, that is operation that flips the state of a qubit if what is called the control qubit is in the state 1, otherwise remains unchanged if it is in the state 0. And then you have a normal rotation. And this is the first layer. The circuit then completes with other 2 layers and then another Adamant gate. Then you have what is called the state vector that tells you what are the probabilities associated to each state of the final state vector. And for instance, given 3 qubits, you are able to create a state vector of 8 dimensions. And in my algorithm, each probability of each state vector tells you in how much it has to move in that particular direction. So for instance, with 3 qubits, I'm able to move a chain up to 8 different dimensions. And this is a good thing because it means that the number of qubits necessary to use for our algorithm with respect to the dimensional complexity is just with the logarithm. And finally, you have the last symbols, which are the measurement symbols just to tell you, okay, measure that qubit and see what is the value associated to that qubit. And so you have the collapse of the quantum information in a classical one. So this is the qubit, for the secret that I'm currently using. And I chose that this particular form just because it is unbiased. It's not giving me a particular specific state which is more probable with respect to all the others. Okay? Of course, if you are curious about other stuff, feel free to ask later or the other days.
Now next speaker is Giacomo. Sorry if I'm wrong with your surname. Nodjoumi. No? Ah, perfetto. Okay, from the Astronomical Observatory of Rome. Okay. So he is presenting us his works about DeepLandforms, a deep learning computer vision toolset applied to a prime use case for mapping planetary skylights.
Yeah, so thank you. And today in this talk, I will try to introduce you on a totally different topic, on a totally different planet, but still related to the artificial intelligence. So I will talk about a tool that I've developed 6 years ago during my first year of the PhD in geoscience. Just a brief introduction. My background is not in engineering, not in mathematics, nor physics, but in geology. So how I reached the artificial intelligence, I don't know, but I was really interested in computer science. So this use case was born because we, as a geologist and also as a humans, we are interested in some mapping. So how to map planetary surfaces like Earth, Moon, Mars, and so on. And one of the most interesting objects or landforms are the pits or skylights, which are just depression. Those depressions, why are so interesting and why we are so interested in those landforms? Well, we were men of caves, we will be back on caves on other planets. Why? Because those depressions are often connected to voids into the subsurface. And voids into the subsurface, we may lead to caves or tunnels or lava tubes, for example. And on other planets, this is so much interesting because we may have access to a shelter, a natural shelter from micrometeorites, from radiation, thermal variation during the day, and also mineral deposits, but also water, ice, and eventually, hopefully, in some planets which still have atmosphere like Mars or Venus, life. We don't know, we've never been there at the moment. There are so many, I think 10 or 15 missions that are planning to go into those tubes, especially on the moon. But there are databases, yes. There are several databases, at least 2 are global databases, one for Mars, one for the moon. And the problem that those are points, are not really giving us much information, just more or less where are those located, some information, but about the sites, but no real area, no real huge parameters. So, and there are a lot of differences between those on the moon, on Mars. Just for example, on the moon, they can reach up to kilometers of width, while on Mars, they can reach up to half of kilometer. So there is really huge differences. And so we have a lot of data about the surface, more than 40 petabytes of only optical imagery from Mars, for example, but also for the moon, at a scale in which we can detect from one single image object more or less bigger than a laptop, so or equal to a laptop. So we can detect theoretically computers on Mars, on the surface, of course. And as well as like laptops on a totally different surface, pits are like popping up on the surface because they're mostly black or circular or elongated, so are very distinctive. And so With this, we have a lot of data, we have clear distinctive surface. Why cannot we use deep learning or artificial intelligence? Seems the best scenario, the straightforward use case, since on Earth we can do this on a cat and dog, for example. So it's really simple, and we have plenty of data. So, well, the reality is not like that, especially for a person that has a different background, but also for people, I guess, that have a background in engineering and wants to move from a theoretical process or a theoretical area to a practical area. So programming, if you don't know programming languages, well, it's hard. If you know programming languages, which one is the best, maybe? Or which one you're familiar with? Or which architecture, which framework? So it starts to become overwhelming by the choices that you can have to start even a simple project. So my goal was to, okay, I don't know anything, like Jon Snow, but why and how I can, or well, where I can reach, how further I can reach by knowing nothing. So what are the architectural frameworks that can be used or more or less used as it is for my problem to detecting landforms on a surface? So as saying before, there are plenty of architecture, plenty of framework or modality and so on. And then we have the other issue. So we're looking at very, very small object in comparison of these largest images. Just for example, here, this is image, it's 38,000 by 14,000 pixels, and our target is more or less very, very small. So like 15 meters, we are looking something like 1,500 meters in an object that has a scale of several kilometers. And we have different features. So we're looking small object in larger images. And how we do that? Okay, we can just do a pure brute force way in which we use those images, very large images, fed to a GPU, a very enormous amount, I don't know, GPU, and then let's do the processing. But, well, this is probably the worst approach, because you have a lot of issues on RAM mitigation or resource computational that are like wasted, because you don't know, you are just testing something that you don't know if you can do it, this approach, or apply this approach. And then you don't know if your architecture is valid, you do the hyperparameter fine-tuning and so on. So typically, probably we will see, or you have already seen something like that, several datasets that are used for the training of object detection or instance segmentation algorithms, they use small images. And how we can do this for those larger images from planetary data? Well, we do the tiling. So, okay, the video is working. So imagine this red dot is our object. It's very small, and we have a very large image. So we can do the tiling, okay, of course. But how we do this tiling? So it opens a new field, let's say, because if our target is very small and our tile is very large, it may well, it may have a lot of context around the target. But if the tile is too small, well, it may not reach or catch all the context, and or cut the target in several sub objects. And so this is something that must be taken care of since larger tiles, the same problem of before, the necessity of larger or higher computational requirements. Smaller tiles don't have the capacity to get the context and then generalize properly the problem. So we have tremendous amount of data, which become more data if you think about the tiling, so more and more data. And then you may have class imbalances because we may have different targets of different sizes, which cannot be classified as one. And so you need to think about how to mitigate with the data augmentation strategies, the generative networks for generating synthetic data, and so on. So there is a lot that is going on. And for a person that is not, of the field, it's very hard to start with. And then we as a geologist, we need the coordinates. So we need to take care also, okay, this is the image, but where on the planet this image is representative. So we need to take care also of the georeferencing. And so in this, we move to GIS software, so the geographic information softwares. But I know this is a lot, and it's even more than this, but I've tried to really synthesize a lot. So I've developed these DeepLandforms that here more or less is simplified as a workflow in which you start with the data labeling. It's a supervised, of course, first approach. Then you move to an image processing utils, which help you to tile properly your larger images or resize them in a lower resolution or try to mitigate some class imbalances in other ways. Then you move to a set of Jupyter notebooks dedicated to do some training and some inferencing while maintaining the geographical information. And all of this is wrapped up in a Docker container or Podman container just to preserve and fulfill the fair, so the findable, accessible, interoperable, and reproducible principle. So to have fair science, let's say. And here are just some examples in which I've trained with all my 5 classes, which I just showed here. Those are the 5 classes. Well, those are even include subclasses, but then, well, it was a mess because the too many classes all at once, it was not able to generalize properly and differentiate from those classes. So I moved to differentiate those classes, and then of course I obtained more higher results, but still were not so sufficient. So there are a lot of missing targets or improper detections. And this is, for example, a usage of mask CNN. So one of the, well, at the time, latest technologies and further improved by Facebook. It was the Detector-2 model framework. And here are some results from the first release, which was based on YOLO, you only looked once, architecture. And it was pretty good because it was kind of capable of detecting craters and pits with a pretty much good results. But then we want to move further because we don't need only to do the detection. We want to do the precise detection, so the mapping. So we had to move to the instant segmentation, which means a detection at a pixel-wise level from the perspective of an image. Then the mask CNN from Detector-2 gave us pretty good result. Even though, if you see the image on the right, there are misdetection, but actually in this time, in this case, actually, this is due to the fact that, we used 2 images that were acquired on the same area, but with different point of view. So the misalignment is due to the original images. And here the results are really good, but still not to be used with certainty, like 100%, this is true. No, because the dataset was small, it required a lot more processing or more optimization. But if we think about that, this was used or obtained just with a network that was prepared, no further optimization, this is really good result. So just take home message. We may to use, or we may tend to say, okay, AI will resolve all of our problems, but it's more complex like this. We may have several problems that can be resolved in different ways, but it's not always like simple, like, okay, let's use AI. We need to think about a lot of steps before even reaching which model to be used. And so the end goal, just to really close, is the publication of our model, our result, our architecture. Yes, of course, we can publish it, but then how people will use that? And in the industry, there is this thing called machine learning operations, or ops, ML ops, which define the standards on how to distribute the algorithms, models, architecture, and so on. And finally, one first step could be to release all our research as notebook containers, even messy notebooks, but still better than having nothing. The most important thing is that you fulfill the fair principles. And so with this, yeah, I concluded. So thank you very much. If you have any question.
So thank you, Giacomo, for this presentation. Very interesting. There is a very quick question for him. No, by Giuseppe.
Okay. Thank you, Giacomo. It was an impressive presentation.
Thank you.
I have a lot of curiosity,
Yep.
so I'm going to just two of them very quickly. The first, do you have some numbers? For example, what is the percentage of false positives and
Yes.
false negatives? And the other question is, what is the typical, I mean, signal to noise level that you have to address in your work?
Okay, so this is a really interesting question about the numbers. I don't have actually right now. Maybe I have something, but you typically the average precision recall and so on are more or less between 80 and 19, depending on the architecture. But really, it depends also on the data that you have used and how much you have trained and fine-tuned eventually the parameters. In this case, with YOLO, I obtained higher results, but was not really reliable in terms of reproducing these on different kind of data set, because these images that I showed are on the highest resolution possible. So the 30 centimeters per pixel images. So all the results, the 80, 90% were on that. When we moved the same model, retrained with the lower resolution model, we got a bad word. So really bad results. So we needed to think about how to readapt it. So it's not really easy to find good result, and that's why to answer your second question is difficult because it depends also on your data set. If you want, in a very specific case, higher resolution possible, okay, that's it. But if you want to have something more global that can be used and reproducible even on different planets or moon, there are a lot of things that you have to do. And for example, just briefly, this is for pits and Skylight, but there are several architectures focused on craters. And those are really, reached step further in the global mapping with average very, very good result, but there are several of those. So even that is really a field of research that is still going on deeply.
Now let's move to the last speaker of this session, to Mario Lauriano from the Astronomical Observatory of Palermo. And he will present his project, the GalRSG project, Red Supergiants on the brink of core collapse.
So, hello everyone. I'm Mario Lauriano, and I'm a first-year PhD student at INAF Astronomical Observatory of Palermo. And it is a pleasure for me today to briefly introduce you to my research project, which is on red supergiants on the brink of core collapse. Red supergiants are highly evolved stars with an initial mass of at least 8 times that of our Sun, and at the end of their lives, they explode in supernova events. Recently, it was observed a dense and inhomogeneous circumstellar medium around progenitor stars. And here, I show you some images of James Webb Space Telescope of red supergiants with the CSM, which is made by gas and dust. And these stars are in Westerlund 1, which is a galactic stellar cluster. These stars can undergo brief but intense mass loss episodes on timescale that ranges from thousands of years to just days before the core collapse, so the supernova event. And in general, these mass loss events are correlated with the nuclear activity of the star. We can detect energy injection from the nucleus to the envelope of the star by anomalies, so detectable modification in stellar light curves. And this is a famous case, which is the great dimming of Betelgeuse of 2020, where the anomaly, so the dimming in the light curve, corresponds to a low luminosity state in images of the star. So, due to the fact that we can detect mass loss, so pre-supernova outburst events, by stellar light curves, we started a panchromatic long-term photometric monitoring campaign with a cadence of a few days on 227 red supergiants, which are the targets of our campaign. And the catalog of the star is presented here in this our IMPRESS publication. And if you want, you can use the QR code to get a look at it. This monitoring campaign is carried by two of most prestigious INAF facilities, which are the VST at Paranal Observatory and REM at La Silla Observatory. The VST in particular is focused on wide fields, in red supergiants which are not clustered, and monitors them every 5 days, more or less, while the REM is concentrated on clustered red supergiants and monitors them every 2 days, more or less. So this is an example, is one of the targets of our campaign. And you have to imagine that, first of all, in orange are the VST data, in green the REM data, and in blue are the data of our facility in Palermo Observatory. You have to imagine that we have 227 targets, but the number of light curves has to be multiplied by the number of bands in which we are monitoring to them, of course. And in general, these stars manifests variability that, physically speaking, could be intrinsic, due, of course, to the radial pulsations of star, photometric convections, and nuclear flashes that are those things in which we are interested in, because are the physical is the cause of the mass loss events of pre-supernova. And we can have also extrinsic factors, as for example, the effect of a binary companion star. So we have already started the analysis of light curves. And first of all, we have simulated 10,000 of light curves divided in 5 classic of intrinsic variability of red supergiants, depending on their periodicity and their amplitude. They can be semi-regular or irregular. And we tried to classify them using machine learning algorithms by comparing different types of them. The result was that the best return was done by the X gradient boost. So the classification of intrinsic variability is the first step in order to eventually detect anomalies on them. So first of all, we have to apply the classification with machine learning techniques on real data light curves by also here comparing different algorithms, as we are thinking, for example, to X gradient boost, or maybe also to recurrent neural networks. At that point, we can look for anomalies, maybe using variational autoencoders, among the semi-regular and irregular variability of red supergiants, constructing an ad hoc alert system in order to eventually follow up putative cases of ongoing outburst events. And on the basis, we have to expand the sample from the 227 galactic targets of now to tens of thousands of targets that are in extra GalRSG. GalRSG is our catalog, so in nearby galaxies. And with this, I conclude. Thank you.
Thank you, Mario.
If you have questions.
Some question? No, Giuseppe is the main.
Because it's 7 o'clock.
Yeah, of course.
Thank you, Mario. Great work. Maybe
you.
I missed.
Yes.
You are using random forest, each booster, and then, but on which features?
Okay, here for this, we can talk about an exercise. We used every single point as a feature. Okay, so we constructed the light curves on semesters. So we have an observing semester and another observing semester that is shifted, of course. We have interpolated the points in order to have the same feature numbers for every light curve. And
So how did you handle the whole, missing data when you don't have?
This is flagged as -999.
Maybe we can talk later, because
Yeah,
we
of
are
course we can
in
go
a different
deeper.
context, but a similar problem we can discuss.
I want to add a thing, if I can, that this is the base also for a trained dataset for the real light curves, because we can simulate the new thousands of light curves in order to train the algorithm.
Yeah. You can also think to use another feature space, for example, statistical feature space, extracting characteristics from the light curves in order to move from your light curves to the feature space, to the feature statistical space. But we can talk.
Yes, we are thinking
next
about
days.
it,
Yeah.
and we can go deep, of course.
Okay.
Thank you.
Thank you again, and thank you to all.